Okay, this should be working. Let's see. Okay, this should be working. Let's see. Amazing. All right. Hello and welcome. My name is Divyansh and I go by Dev, and my intention is to learn and try to master deep learning, which is everything to do with neural networks. This happens to be a great time to learn neural networks because almost every industry is being impacted mostly positively by AI. And it's not only expeditious to do so, but also very interesting to do so because it turns out that these models are very cool when you try to understand them from the ground up and trying to understand like why and how they work. Of course, these questions are fairly difficult to answer because um, there's some sophisticated math that goes behind them, at least the ones that are at the state of the art, but it's not super difficult to at least gain a working understanding of the ones that at least inspired the state of the art. So like the first few transformers, like the first ones that ever came out were like from companies like Google, which released a paper called Attention is All You Need, where they sort of debuted the attention architecture, the transformer architecture, and the core innovation was the attention mechanism, which we will learn about later. And my intention is to use these videos and these live streams and the series as a way of not just keeping myself accountable to all, but also to document my journey and try to figure out my blind spots in how I learn so I can even learn better and faster. And hopefully, if someone follows along, if you're following along, I really hope it's beneficial to you. So, with that said, let's get started. The setup is as follows. This is my iPad, and it's yeah, I can do stuff on it. I can write stuff on it. So hopefully, um, I can even do this laser pointer thing, which is super fun. But yeah, hopefully I can use this to sort of explain and draw stuff as I go along. Of course, I've not written much because I just started, but hopefully I can. This can be useful. The intention here is super simple. In this live stream, we will try to understand the transformer architecture and hopefully code one from scratch. I have this Jupyter notebook going, where I have basically just started in like rudiments, and like from the basics, and I've sort of distributed this transform model into its component parts, each of which we will uh try to learn in detail, and then of course training and inference, which we will get to later, hopefully. Okay, and the guiding principles here are to reach state of the art as soon as possible, but without compromising understanding or comprehensiveness of the content that we learn. And the second thing is to just deconstrain and expedite our learning. So whenever we're like stuck at something, just ask ChatGPT, which is like the sort of ironical, funny, recursive thing where I'm sort of asking a large language model how to make a large language model. But that's sort of the cool thing about it. And then, of course, learn by doing. So all understanding is cemented in application, I believe. So we will, of course, be coding side by side. I have a good compilation of the resources that I will be using. Hopefully they can be helpful to you. And yeah, with that, let's get started. So to give you a bunch of context, um, attention is all you need is this paper right here. This actually is a fantastic website. It's just archive, but you can just change the archive into alphachive, and it will give you this window where you can ask the paper questions. And of course it gives like semantic recommendations of papers too, so you can like search up things about, oh, using transformers to, I don't know, uh actually let's do uh text to 3D models. Yeah, so you can do semantic search on queries for papers, and it will give you some of the best recommendations, at least I've come across. So yeah, super useful website. Here is where we are learning about attention is all you need. Now, the paper is not too difficult to follow if you just sort of follow the linear algebra of it all. But I will say the while the diagrams are very informative, they could have been easier to understand because in this diagram you have no way of knowing what these three arrows mean without reading the paper or even like just trying to understand the diagram. The descriptions could be much more descriptive, I believe. But anyway, hopefully I can sort of help in fill in the gaps while I learn. And yeah, so this is the main innovation of the paper, which we will hopefully come to. And by no means am I claiming to be an expert here. I'm learning as much as maybe you are. I just happen to have these resources already good to go so that I can reference them. And by doing this, I hope I can give you some of these resources as well. I realize I'm being too verbose. Let's just begin learning. Okay, so in Attention is All You Need, they sort of introduced this transformer mechanism to do a translation task. Yeah, right here. And I think they were translating between texts of two languages, so like English to German translation task, and then yeah, English to French. So this is almost like I believe this is sequence to sequence, which is you provide one sequence and then you uh, uh, output a sequence. Most transformer models are sequence ones. Now they're being used in different things like um, I suppose the attention mechanism is being used in image generation also, I believe, along with diffusion modeling. But I don't completely understand that, so I will refrain from saying more. But yeah, but the key distinction here, and maybe something like ChatGPT, is in this model, there's an encoder, and ChatGPT and Gemini and Anthropic are mostly just decoder-based architecture. So this is the encoder, this is the decoder. All that ChatGPT does is use this part as the decoder. Yeah. So that's kind of the intuition here, and we'll understand why. But yeah, this is the equation for the attention for one single attention head. Um, a lot of deep learning can be understood by just following the dimensions of the outputs of systems. And you can usually just backtrack to, okay, this is why this makes sense. But yeah, so you get attention heads like this. You do multi-headed attention by concatenating every single head like this, where each head is doing attention on uh, these matrices, all of which are learned, I believe. Yeah, yeah, all of which are learned. Yeah, this is what attention QKV looks like. Okay, so let's get started from the beginning. I came across this great video that I hope to be following and sort of giving my commentary on it as I understand it, and then also coding side by side. It's by this YouTuber and machine learning practitioner called Umar Jamil. He is absolutely fantastic. His sort of paper reviews, in-depth explanations are genuinely some of the best I've ever come across. So yeah, super recommend. But with that said, let's start doing this. Um, yeah, coding a transformer from scratch. Attention is all you need. Explanation. Okay, so in here he's doing an image translation task. I do want to do a complete decoder only architecture, but I suppose this is important too, just to follow because this will give us everything that we need to understand decoder only transformers as well.
This one part is
If anything, they're simpler than the transformers in the attention to is all you need paper. Okay, I've watched this much, but I forget a ton of it, and I've coded none of it, so it's good to start from the beginning.
Hello guys, welcome to another episode
Okay.
about the transformer. In this episode,
I wonder if it's like doing double audio. Let me check real quick.
in this episode
I wonder if it's like okay.
about the transformer. In this episode,
I wonder if it's like do no, I think it's fine. I believe it's fine. Okay. Let's just do it. And let's hide so I use this YouTube extension to hide a lot of these distractions. So hide video sidebar. Do I hide comments? Yes, I hide comments. They're usually not useful. They're just mostly appreciative of this video, which I am too. And yeah, okay, this makes sense. Hide shorts all the time. Yes. Um, subscriptions. Sure, why not? Okay. Yeah. All right. All right. Okay. Let's keep
we
going.
will be building the transformer from
Just reducing distractions here.
scratch using PyTorch, so coding it from zero. We will building the model, and we will also build the code for training it, for inferencing, and for visualizing the attention scores. Stick with me because it's going to be a long video, but I assure you that by the end of the video you will have a deep knowledge of the transformer model, not only from a conceptual point of view but also from a practical point of view. We will be building a translation model, which means that our model will be able to translate from one language to another. I chose a dataset that is called Opus Books, and it's sentences taken from famous books. I chose the English to Italian because I'm Italian, so I can understand and I can tell that if the translation is good or not. But I will show you which point you can change the language so you can test the same model with the language of your choice. Let's get started. Let's open the IDE of our choice. In my case, I really love Visual Studio Code, and let's create our first file, which is the model of the transformer. Okay, let's go have a look at the transformer model first, so we know which one part we are going to build first, and then we will build each part one by one. The first part that we will be building is the input embeddings. As you can see, the input embeddings take the input and convert into an embedding. What is the input embedding? As you remember from my previous video, the input embeddings allows to convert the original sentence into a vector of 512 dimensions. For example, in this sentence, your cat is a lovely cat. First, we convert the sentence into a list of input IDs, that is, numbers that correspond to the position of each word inside the vocabulary. And then each of these numbers corresponds to an embedding, which is a vector of size 512. So let's build this layer first. The first thing we need to do is to import torch. And then we need to create our class. This is the constructor. We will need to tell him what is the dimension of the model, so the dimension of the vector. In the paper, this is called the model. And we also need to tell him what is the vocabulary size, so how many words there are in the vocabulary. We save these two values, and now we can create the actual embedding. Okay, actually PyTorch already provides with a layer that does exactly what we want to do. That is, given a number, it will provide you with the same vector every time. And this is exactly what embedding does. It's just a mapping between numbers and a vector of size 512. 512 here in this our case is the D model. So this is done by the embedding layer and n.embedding and vocab size and D model. Let me check why my autocomplete is not working. Okay, so now let's implement the forward method. What we do in the embedding is that we just use the embedding layer provided by PyTorch to do this mapping. So return self.embedding of x. Now, actually, there is a little detail that is written on the paper. That is, let's have a look at the paper actually. Let's go here, and if we check the embedding and softmax, we will see that in this sentence, in the embedding layer, we multiply the weights of the embedding by square root of D model. So what the authors do, they take the embedding given by this embedding layer, which I remind you is just a dictionary kind of layer that just maps numbers to the same vector every time, and this vector is learned by the model. So we just multiply this by math.sqrt of the model. You also need to import math. Okay, now the input embeddings are ready. Let's go to the next module. The next module we are going to build is the positional encoding. Let's have also a look at what are the positional encoding very fast. So we saw before that our original sentence gets mapped to a list of vectors by the embedding, the embeddings layer. And this is our embeddings. Now we want to convey to the model the information about the position of each word inside the sentence. And this is done by adding another vector of the same size as the embedding, so of size 512, that includes some special values given by a formula that I will show later, that tells the model that this particular word occupies this position in the sentence. So we will create these vectors called the position embedding, and we will add them to the embedding. Okay, let's go to it. Okay, let's define the class positional encoding.
Okay, so I stopped here and try to demystify or try to demystify what he just did. So obviously, our transformer like ChatGPT takes some text and outputs more text. But how does it do that? Like, how does a transformer know what text means? Like when I say, okay, I am a student studying transformers. How does it make sense of all those words? So obviously there is we have to since this is a statistical model, we need to convert this text into numbers. And how do we do that is the main question here. And the answer, of course, is input embeddings, and they're combined with positional embeddings. Input embeddings strictly convert the textual representation of text to a numerical representation of text and then vectorize them, which is just to assign a bunch of numbers in a list of sorts to each broken part of the textual representation. So if I say, I love learning about transformers, and let's say I was somehow breaking my sentence down by each of the words, I love learning about transformers. I have 5 words in my sentence. These 5 words would each have a unique number assigned to them. So let's say in computer science and we start counting from 0, not from 1. So I has an index 0, love has an index 1, learning has an index 2, about has an index 3, and transformers has an index 4. Now, each of these indices are then mapped on uh, to a vector of size that is usually determined by the dimension of the model, which is what he's doing here, which is what he's like referring to here. And you later come to know why this dimension is sort of useful, but you can almost think of this as like the higher the dimension of the model, the more information you can encode in any single vector representing a word. So the D model for this, the dimension of models, the model dimension for this model that he's coding up, I believe is 512. So 512 numbers in the vector that we're assigning to any one word. And of course, you will think that, okay, if I just make that vector 1024 numbers long, which is exactly twice, you can encode about twice as much information uh, in the vector, which is a rudimentary way of thinking about it. I don't actually know if information scales linearly with numbers in a vector, but that's a naive assumption. That's at least intuitive to me. So with that said, let's literally. So we've understood what he did. Now we will try to code it up without looking at his code until we are done with the input embedding class. So, and I'll also, of course, explain. I have like a sort of diagram done for the input embeddings here. But yeah, just to show you what he's trying to do, um, basically, input embeddings are implemented as this nn.embedding class, which is a tiny wrapper over a 2D matrix. It's literally a 2D matrix with dimensions, vocab size by D model. Vocab size is the number of rows. So the number of rows is the vocab size, and D model is the number of columns. So you can say something like, if I was using a word level tokenizer, so breaking my sentences down by words, each of these words would be called a token, which is like how we're breaking the sentence down. And each of these words would have a D model long column vector. which is what I was telling you about. So it happens to be 512, like 512 in this case. But if it was twice as long, it would be 1024 numbers long, and so on. So if I were to say the attention mechanism is cool, the would have 512 numbers assigned to it, somehow unique to it. Um, Attention would have another 512, mechanism another 512, and so on and so forth. Now, yeah, I'm right. So the 512 is the D model, and then 10,277 is the vocab size of the tokenizer that I was using in the decoder only transformer, but doesn't have to be here. We will see how we tokenize here. I actually don't know. But yeah, that's kind of what we're doing with input embeddings. Super simple, not too much to be worried about. Um, okay, let's actually create a new notebook. Uh, yeah. Uh, Attention is all you need dot IPYNB. That sounds like a hard to pronounce name. Let me change that and say vanilla transformer. Actually, that's also a stupid name. Let's just do transformer dot IPNYNB. Okay, so let's do input embeddings. And then let's make it this. I try to do conda for my environments. I like it. Of course, we need to first import some important libraries. So let's do that first. Import torch, uh, import torch dot nn, which is the main module, as nn. Up, import math. Um, uh, what else? Yeah, I think that's good for now. Let that run. Class input embeddings. Input embeddings. They should inherit from the nn.module def init. Oh, this is excessive. Um, yeah, we're just calling the super method so that it can sort of call the methods in methods and attributes of the parent class, which is nn.module. Um, and then we're also doing self dot vocab size. No, which ones did we define? We definitely did the embeddings to be nn dot embedding. Uh, and of course we need to define the it as vocab size for rows, which is the number of embeddings, and the dimension of the model should be d model. Yes. Now we need to define what self dot vocab size is and self dot d model is. So I believe it's 512, and vocab size I'll have to check. But I suppose we don't do that right now. We use those as parameters in the self function. So we add them as parameters to the self init function. So while we initialize these input embeddings, we can just add them as parameters. Okay, now there's the forward method, which is how data flows in any object that is a child of the NN module class. So this forward method is a necessary method for an NN module class or any instantiation of that class or a child of that class, because PyTorch is basically just an automatic differentiation engine. So it just does numerical differentiation on all the nodes in this graph of computations that it does. um, and that graph is basically defined by these a bunch of forward functions. So as Omar Jamil said, Professor Jamil said, we just have to return self dot embedding. Oh, we also need to add self parameter here. Self dot embeddings. Let's do self dot embedding. I believe that's the right one. Doesn't really matter. Uh, X. Um, yeah. Get item method not defined on embedding. Why? Hmm. Okay. Let's just do this times math dot sqrt the model. Oh, self dot the model. Why is this not doing it? Um. Oh, it's a function. It's a function. It's not like a. It's not a subscriptable. Not subscriptable, but indexable. I suppose this is literally equivalent to that operation. They could have just done that and they would have been fine. I suppose they just didn't have. Let's actually check out what the embedding class looks like. Okay, embeddings. Okay, init x. Okay, forward embedding. All right, max node. Okay. Oh, what is this inherit from? Module. Okay, parameters. Okay. Yeah, it defines a parameter of sorts, which is basically a torch tensor um, of num embeddings by embedding dimension. Yeah, so it entirely becomes a parameter if weight is not known as assert list. Okay, shape of weight is not matched. Okay, fair enough. All right. Yeah, that makes sense. So it just creates a 2D array, all of which are trainable parameters, which means they can be done differentiation on and their values can be changed in a back propagation step. Okay, that makes sense. We should run this cell. Okay, now we are doing positional embeddings. This is also a child of nn.module. We also need to define the init function for this. Of course, it's excessive because why would it not be? And then we also need to do forward with these um, pass, self, x. Okay, okay, let's keep going, shall we?
And we define the constructor. Okay, what we need to give to the constructor is for sure the d model, because this is the size of the vector that the positional encoding should be. And the sequence length, this is the maximum length of the sentence. And because we need to create one vector for each position. And we also need to give the dropout. Dropout is to make the model less overfit. Okay, let's actually build the positional encoding. Okay, first of all, the positional encoding is we will build a matrix of shape sequence length to d model. Why sequence length to d model? Because we need vectors of d model size, so 512, but we need sequence length number of them because the maximum length of the sentence is sequence length. So let's do it. Okay, before we create the matrix and we know how to create the matrix, let's have a look at the formula used to create the positional encoding.
So I sort of missed why. I mean, these are just like he's just defining the init method, and now he is making a, a tensor or just a matrix of positional encodings, which has to be in the dimension of the maximum sequence length that the model can process at any single point in time. times the dimension of the model, because each of those words in that sentence would still need to correspond to a vector in the embeddings which we defined here. Okay, that makes sense, but I will sort of rewind just for
size, so 500. So that's 12,
clarity's
but we
sake.
need sequence length number of them because the maximum length of the sentence is sequence length. So let's do it.
This is Celsius, by the way. This is great.
Okay, before we create the matrix and we know how to create the matrix, let's have a look at the formula used to create the positional encoding. So let's go have a look at the formula used to create the positional encoding. This is my previous the slide from my previous video, and let's have a look at how to build the vectors. So as you remember, we have a sentence. Let's say in this case we have 3 words. We use these 2 formulas taken from the paper. We create a vector of size 512 and one for each possible position, so up to sequence length.
Okay, so this is interesting. This is very interesting. Okay, so the reason why we need to do this in the first place is because transformers are built in a way where they're almost like extensions of recurrent neural networks that came before them. And the main innovation is that transformer models can ingest a lot of information at once in a parallelizable way, which means they can be trained pretty efficiently on GPUs, because GPUs are optimized for matrix operations like matrix multiplications. And since in a transformer, many parts of the same sentence can attend to other parts of the same sentence, um, they can be made into matrices which just multiply with each other, and that sort of learning happens there. Now, in each of those, now each of these tokens, let's say, um, has an input embedding, but the transformer has no real way to distinguish between the position of this token and the position of this token. So these embeddings are sort of deterministically calculated using these formulae, and they're just imposed upon these input embeddings, I believe, by just adding literally element wise addition. So input embedding vector has the same dimension as this positional embedding vector, and it's just added. And somehow we hope that in a lot of training examples, the model to somehow learns that okay, almost like basically backtracks this addition operation of this positional vector, uh, embedding vector, to see that okay, this, if it somehow contains elements close to what this positional encoding entails, um, it sort of has this position that this vector embedding, position embedding corresponds to. So if let's say for position one, uh, for position one and I being, let's say, 2, right? Position 1, which is the position of the token, and the I being the index in the positional embedding for that token. So this is position 0. Let's say position 0 is your, position 1 is cat, position 2 is. So for position 0, when I is equal to 2, so 0, 1, 2, right? PE02. Um, oh, wait. No, no, no. I is 1, which means yeah, for I to be 1, it would need the position. And so for the arguments in this PE function would be 0 comma 2, which would mean this one right here. So somehow the formula would look something like, if I were just to do that on my thingy, iPad, uh, it would mean PE, uh, Suppose do I equals something like it's sine, I believe. Um it's not sine, it's cos upon sine something something over something. What is the oh, I was so far off. I also don't understand where they came up with this formula, but I understand why they came up with these because they're super deterministic, and of course, no single uh no single I value within a vector and no single I value between position vectors will ever be the same using this formula. Uh, yes, because as the position increases from 0 to 1 to 2, the frequency of the argument increases. So, as of course, you must have maybe studied in high school, sine x looks something like this. Let's say, sorry, this is the axis. Sine 2x is a lot more squished. So it's sort of like this. It's almost twice as the wave is almost twice as frequent. So it's sort of the intuitive way to describe it is the amount of folds or the amount of complete cycles. So let's say if we were to say this is one cycle, uh, this is one cycle, it sort of does twice as many of those cycles in the same sort of distance, right? Like right here and right here. While these, uh, oopsie, while these points are about the same on the x-axis. All right. So of course, if we are making this 1000 um 2i upon d model, d model, what the, okay, um yeah, so as position increases, the frequency increases, but as of course d model stays constant, as I increases, the denominator also increases. So denominator increases, and at some point, I believe, of course, the positions increase at a faster rate. So because I can only have, it can only like 2i can at max be d model. So this denominator right here can at max be 1,000, because most of the time, well, basically all of the time, 2i will always be lesser than d model, because I starts from 0 to um, d model by 2, I believe, right? Because each each position embedding vector is also constrained by the input embedding dimension, which is 512. So yeah, so what we're sort of doing is, as this I as this I also increases the within one single position embedding vector, the model gets less frequent. Um, so it sort of goes the other way around. So it starts frequent. Um, somehow it starts frequent because when 2i is small, uh let's say I is something like 20. So 2i would be 40, and of course d model we're taking to be let's say 512. 40 divided by 512 is, let's calculate, 40 divided by 512, 0.078. Okay. Um, 0.078. So obviously 0.078, uh, that's 1000 times 0.078. That's a very, very small number. Let's do the calculation actually. 1000 times 0.078, 1.17. I'm kind of crowding the space here a little bit. I wish I took these calculations down, which I can do now. Uh, what? Okay. Okay. And then delete this. Okay. So this means this is 1.171. Now, of course, this is when I is equal to 20. Now, just assume, so if you just want to visualize real quick, in this position embedding vector where the last, where the first one is 0, where the last one is number 512, this one is somewhere here. This I is somewhere here. Now, let's take the example of I equals 40, which is somewhere, let's say here. Um, right here, right here. And 2I is 80, and D model, of course, is still 512. Uh, so 2I upon D model would become 80, oh, 80 upon 512, which is exactly the double of 0.078. So something along the lines of 0.156. So this would give 1000 times 0. Just to check real quick. 80 divided by 512, 0.156. Um, and then of course 1000, basically to the power of 0.156 is equal to 2.93. Okay, 2.93. So now we have the denominators. We have the denominators of our sign fraction here. So we have this part for, of course, I is equal to 20 and 40. Yes? Now let's do the fraction. So uh we have the 1000 times this 2I upon model. Now let's do the position upon 1000 times 2I times D model up, which let's take the position to be 4, which is the fifth token. So position to be 4 means something like this. I, which is 0, find 1, transformers 2, 2, 3, B, 4, really cool, 5, 6. Yes? Now, of course, we have input embeddings for each of these. Dot, 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 dot. These are input embeddings, which are different from position embeddings. This is the one we used, or we calculated from the nn dot embeddings one, the input embeddings class. And then, of course, the position embeddings. These are, of course, the D model is 512, 512. And this is similar for all of these. And such is the case, such is the case for position embeddings as well. Position embeddings as well. where the D model is, oh, D model, oh, oh, is this, okay, cool. Now let's take the position to be 4. So the position 4 would mean we're in this one right here, and we're trying to calculate this vector right here, the position vectors. So for each of these i's, of course, each of these i's, right, um, we are calculating the 2i, which is the even positions. So 2i would mean 2 times 0 is 0, which is here. 2 times uh, 2 times 1 is 2, which would be here because this is 1 and this is 2, which would be here. So we're skipping this and every single odd numbered index to do every single even number index, which is why we're using sine. And then when we come to odd number indices, we'll use the cosine function. So let's say the position is 4. So we did that. And of course, position 4, within the same token, within the same token, we're calculating the exact number for index 20 and 40, which amount to be actual indices 40 and 80 in the vector, because they get multiplied by 2 so that we can get the even numbered index. So we're trying to calculate something like what the number is for 40 and what the number is for, let's say, 80. And of course, the dimension of this model is 512. So let's try to do that. 4 times, this is for I equals 20, this is for I equals 40. 4 times, we got this as the denominator value, 171. We got 4 times, this is the denominator value, so we get 293. This is separate from this. um, 4 upon 1, 4 divided by 1.171, 3.416, let's say 3.416, and 4 divided by 293, 4 divided by 2.93 is 1.365, 1.365. Okay, so now we just need to put this number into a sine function and see which one is more frequent or which one has the higher frequency. And of course, uh, we sort of learn in even simple like circular motion classes or angular momentum classes where it's almost like 2 pi uh, uh, f or something, um, where the f is the frequency. And as this number increases, this also signals, because since 2 and pi are constant, that the frequency is increasing. So sine 3.416 has a higher frequency than sine 1.365. Um, yeah, and the values of these sort of the values of these numbers is not super duper important, in the sense that, of course, the value of the function itself doesn't need to be high. Like the value of this function itself does not need to be lower or higher than the value of this. But we know that just by looking at the arguments inside of these sine functions, that the frequency of sine 3.416 is much higher than the frequency of sine 1.365. And that change in frequency can be used within the same vector to determine the position of a number within the position vector, and of course across many, many, many vectors. As the position argument changes, it can be used to infer changes in position. So how do we do that? Um, of course, we can look at sine 3.416. We get minus 0.27. Yeah, we get minus 0.27, and sine 1.365, sine 1.365 is 0.97. So of course, uh, counterintuitively enough or not, uh, the sign of this, the value of this function is actually higher than the value of this function, but that really does not matter. All we need to see is how these values somehow change for the same I values across positions. So we calculate for the position 4. Now let's do the same thing for position 5. So we already have the denominators um, for these I positions in a same vector. We just need to change the position argument. So we can just do something like this is for position equals 5, sine 5 upon this is I equals 20, this is I equals 40, position equals 5. Sine upon 1 point, what was the thing? 1.171. 1.171. I'm looking at this number right here. 1.171. 171. And then I'm looking also at 5 upon 2.93, I believe. That was, yes, right here. Um, yeah. Yeah, I should use the same decimal points, but that really doesn't matter here. I'm just trying to show this for demonstrative purposes. So let's actually do that. Um, Sine 5 divided by 1.171 is minus 0.90, and sine 5 divided by 2.93 is 0.99. So let's almost compare the vectors of the position embedding for position equals 4. And of course, the position 5 was, this is position 4. So position 4. So let's use the same color. Let's try to at least. Position 4 is B. Position 5 is really. So position equals 4. Position equals 5. The PE of this position, I want to keep the colors constant. So let's draw the vector out here. Let's also draw the vector out here. Um, we calculated the numerical values for uh 2i equals 40. So the 40th element of the array of the embedding, 512, 512. We also had 40 here. 2i equals 40. We also did 2i equals 80 right here somewhere, and also the same thing for 2i equals 80 for position 4. This came out to be minus 0.27 and 0.97, minus 0.27 and 0.97, and this came out to be 0.99 and minus 0.90. Right. So, as we can probably see that even between position embedding vectors of two almost like basically consecutive positions of words, we're somehow encoding different positional information between two positions. And then when we add that into the input embeddings for um, B, I think that was B. And really, the transformer somehow parses that information as, somehow differentiating these tokens and having different positions. Yeah. Also, the sort of point I was making with this stuff is this value right here, this value changed a hell of a lot more than this value right here. The delta here was negative um, 60.63, right? And the delta here was just 0.03 or 0.02. If we were to just calculate the absolute value, of course, we just get rid of the negative sign, 0.2, 0.02, 0.63 is a hell of a lot more than 0.02. So we can almost assume that as these indices go down, the differences in values at any one single particular index across positional embeddings gets lower and lower and lower. So it's almost imposing a lot of change on the first few numbers within the positional encoding, which is usually all you need, which is usually all with like a lot of data, all that the transformer needs to really distinguish between position. Um, yeah, so it's almost like you can think of these positional embeddings as waves almost, where the higher up you are, the sort of more frequent these changes are between the same indices between positional embedding vectors. But as you go down the indices in positional encoding vectors, these sort of changes get a lot slower. So they don't change much. They change a lot more uh, in the first few indices than in the last few indices of the of any positional encoding. Now, this brings with it a few problems, um, which we will obviously discuss. But a simple problem that you can probably see is this almost makes the last few indices kind of useless. If they don't differ by much, they're not carrying a hell of a lot of different like information, which sort of is useless and is sort of useless information to the transformer because it's not really adding differentiate like value that can easily be used to differentiate between two positions or tokens at two different positions, right? It would be fantastic if we had more easily differentiable, not differentiable, differentiatable, or like values that can be easily differentiated, even at the last few sort of indices of any positional embedding, which I believe this problem is somehow solved by rotary positional embeddings, rope, which we hopefully will come to learn soon enough. But this is the sort of problems that exist. Of course, like if you were to find the frequency uh, of a sign of these values somewhere in the middle of these two, you'd find something like in the intermediates or something like this. Yeah, so it kind of does this a little bit. And of course, we somehow just did calculations for even indices, but likewise is the case for cosine values, where literally the only thing that changes is the 2i becomes 2i plus 1 because it is accommodating odd numbers. So if I was 1, 2i plus 1 would become 2 times 1, which is 2, plus 1 becomes 3. So I equals 1, 2i plus 1 becomes 2 times 1 plus 1 equals 3. So that would encode for the third index in um, in the vector. And of course, for index number 1, you can just keep I equals to 0, which would mean 2i plus 1 becomes 2 times 0 plus 1, which is just 1. And of course, so on and so forth. This would become 5, 7, 9, 11, so on and so forth. And of course, just 2i goes from 0 to 4, 6, 8, 10, and so on and so forth. So it's almost like this. Yeah. And then combined account for each of the indices of each of the position embedding vectors. This is a very long-winded way of saying we need to impose positional information onto input embeddings, and we can do that deterministically by using very, very simple formula. Um, yeah, I hope that was sensible enough. Okay, let us keep going. Oh, almost opened a new video. Oh, almost opened another new video. Okay.
And in the even positions, we apply the first formula. In the odd positions of the vector, we apply the second formula. In this case, I will actually simplify the calculation because I saw online it has been simplified also. So we will do a slightly modified calculation using log space. This is for numerical stability. So when you apply the exponential.
Okay, fantastic. They used 10,000, I used 1,000 in my example. Doesn't matter. Same intuition.
And then the log of something inside the exponential, the result is the same number, but it's more numerically stable. So first we create a vector called the position that will represent the position of the word inside the sentence.
Also, if you wanted to think of this analytically, as if we've not done that enough, um, what I was saying with respect to 2i upon d model as as d as 2i approaches d model somewhere here, it approaches the value of yeah. So as this approaches the value of 1, this entire um, denominator approaches the value of 1,000, which sort of brings down the value of this entire fraction. And by bringing down the value of this entire fraction, which is the exact input parameter to the sinusoidal function right here, it's reducing the frequency, thereby making the waves more flat. And that's why we observe lesser differences between values of the same index in two different positional encoding vectors that even happen to be consecutive. So of course, 4 and 5 showed so little difference. Of course, 4 and 6 would show a little more difference, but not much more for the same index position. And 4 and 494, let's say, if that was part of the sequence length, would show a fair bit of difference at I equals to 40, but not as much difference as I equals to 20, which would make 2I equals to 40, and 2I at the I equals 40 would mean 80. But we're getting lost in the details here. I really hope I can transmit. I could have I really hope I can what I really hope I could transmit what I was trying to say. Okay. Actually a fair actually a good diagram. This could be used to explain uh, positioning encodings. Anyway,
And this vector can go from 0 to sequence length -1. So actually we are creating a tensor of shape sequence len to 1. This is wrong.
Column vector.
Okay, now we create the denominator of the formula. And these are the two terms we see inside the formula. Let's go back to the slide. So the first tensor that we built, that's called position, it's this pos here. And the second tensor that we built is the denominator here. But we calculated it in log space for numerical stability. The value actually will be slightly different, but the result will be the same. The model will learn this positional encoding. Don't worry if you don't fully understand this part. It's just very special, let's say, functions that convey this positional information to the model. And if you watch my previous video, you will also understand why. Now we apply this to numerator and denominator to the sine and the cosine. As you remember, the sine is only used for the...
Okay. So the diff term is being computed in the log space for numerical stability. I don't know why that is more numerically stable, but I suppose. Okay, let's try to parse this out. Torch.xp is nothing, exp is nothing but e to the power of something. So e to the power of this column vector, which means every single element wise, e is being raised to uh, minus log upon d model. Okay, don't know what this means. Oh, it's the same equation. It's the same equation. So let me write this equation down. Torch.exp, torch.arrange 0 d model um, 2 dot float times minus math dot log 1000 divided by d model. Okay, all right. So let's parse this out. Um, this here is nothing but yeah, why is there a 2? Why is there a 2? It should be a 1, I believe. Yeah, I think that's a typo. It should be seek length 1. Let's actually look at torch.arrange. Um, oopsie, torch.arrange syntax. One-dimensional vector. Start 0, end something else. Step 1. Okay. Okay. See. Position div term. Yeah, so torch should arrange. Oh, this is for the even positions because it's stepping from 0 to 2 to 4 to 6 to 8 to 10, etc., etc. So this is sort of the formula for even positions. So if I were to say this, yeah, so it's kind of going from 0 to 2 to 4 to 6 and so on, right? This is just a column vector basically. um I mean, I suppose this is a row vector, but this is easier to visualize, so I'll do that. um a column vector would have the unsqueeze function. Oh, I was not even showing it. Yeah, so this is a column vector. This represents a row vector. If it was a column vector, it would have the unsqueeze in uh, the first argument of the dimension, which is the column that you want to unsqueeze by. But yeah, it's easier to explain, so I'll just use a column vector for now. But you can imagine this being a, a, a 512 element list where we're basically exponentiating each of these elements by this um, argument. Yeah? Okay. So what does this mean? We're just exponentiating torch dot arrange. Yeah. So arrange is also deterministic list generator where it's generating a list. I can show you. Uh, yeah, so arrange 5 would look something like 0, 1, 2, 3, 4, 5. Arrange, this is the step, so it does 1, 1.5, 2. So torch dot arrange something like, actually I should have just shown you in the Jupyter notebook. It's not too hard. Torch dot arrange 0, 5, 1, 2, 2 would look something like 0, 2, 4, 6, 8, 10, all the way to 510. There you go. Why are we doing this? Because of the even positions, and then we can also do the same thing for the odd positions. So something like um, we can start from 1 to 511, and the step function would also be 2. The step would also be 2, something like that. So 1, 3, 5, 7, all the way to 511. Um, yeah. And then we're exponentiating this. Torch.exp, oopsie, which is just putting each of these to the e. So it would look something like, um, so if this is the array, so if this is the array with this, so this is 0, 2, 4, 6, 8. This would just mean exponentiating this would just mean um, something like E0, E2, E4, etc., etc., etc. And of course, this is 1, this is, yeah, this is 1, this is whatever, and this is whatever. Okay, we can actually do that. When we do that, oh, yeah, so 1, then this, then this, and this. And then, of course, it becomes big enough where e to the power 512 becomes infinity, basically. And all those values are just termed infinity. And that's numerically stable. Actually, that's not numerically stable, but infinity is just beyond a certain threshold of number of values. Our computers just think they're infinity, which is what's happening here. Now, why are we then multiplying each of these values by negative log of 1,000, right? Or 10,000. Ah, yeah, 10,000. Should have done that properly. Okay. Divided by the model. Wait, actually, is that right? That is right. Okay. Okay, so this sort of makes sense because when we multiply, let's say, e to the power of a position, or let's say 2i, which is what's happening here, times negative negative log 10,000 upon d model when we're like sort of exponentiating the numerator and the denominator. This just becomes this just becomes negative 10,000 upon e of d model, right? But do we want that? Mm, no, we don't want that, because then it would, we want the final function to look something like the the log of e to the 2i upon d model, um the whole times 1,000 or 10,000, whatever. um no, that's not true. You need that to be a power of 10,000, right? Sine cos 10,000 2i upon d model. Yep. Okay, we're trying to figure this part out right now. So when transforming this stuff, this should look like, yeah. So this should look like, if we're doing e of e to the mm,
The even positions and the cosine only for the odd position. So we will apply it twice. Let's do it. So apply. So every position will have the sign, but only, so every word will have the sign, but only the even dimensions. So starting from 0 up to the end and going forward by 2 means every from 0, and then the number 2, then the number 4, etc., etc.
okay. So before we do the exponentiation, we're actually doing the logarithmic multiplication first, and then only can we apply the exponentiation at all. That's where I went wrong in my analysis. So it would look something like this, where each of these numbers, 0, 2, 4, 6, so on, would then be multiplied by negative log 1,000, sorry, 10,000 divided by the model, which makes sense to me because we want something to happen where it becomes this, so that we can then okay, that makes sense. Yes. Okay. This makes sense. So this, each of these is a 2i. When multiplied by this becomes 2i times negative log 10,000. Negative log, if we want to simplify that, becomes 1 upon log 10,000. So this almost becomes uh 2i upon d model uh upon log 10,000, which then exponentiated, right, becomes uh Wait for it. Wait for it. Okay, so it's a product, so this comes out. Um, so it becomes 1 upon log. Oh my God. I keep forgetting to switch. So what I did is each of oh, what's going on? Okay. That I did not mean to do that. Anyway, um give me 1 second. Yeah, definitely did not mean to do that. Anyway, um yeah, so as I was saying, we can then do this, do I upon d model, and this we know is just negative log. So we can almost do this. So we can transfer the negative outside, right? We can almost, yeah, so this becomes that. We can transfer the negative sign outside. Um and this just becomes log 10,000. E to the log of anything is just the number itself. And this becomes this. And of course, with a negative exponent, it becomes this, 2I upon d model. And then for each of the positions of positional embeddings, so let's say 0, 1, 2, 3, 4, each of these is a pos. We just put pos in and then do sign. And then we have the numerical values of all of the uh, even indices for all of the positional embedding vectors in a position embedding matrix. Okay, that should sort of demystify the code that he just wrote there. Yeah, I kind of had yeah, I was I was trying to deconstruct this a lot because um yeah, I completely did not understand this before I sort of laid this out myself. I'd only watched a bunch of videos, but I'd gotten a sensible idea, but not enough to flesh this out by any shot. But I'm very glad that I did because this is really cool stuff. Anyway, let's keep going. We've only crossed 10 minutes of the actual video, and it's already how long? 1 hour and 23 minutes. You are welcome. Okay,
Position multiplied by if term. Then we do the same for the cosine.
so for each of
In
the
this case, we
vectors.
start from 1 and go forward by 2. It means 1.
Yep, so exactly what I did here. Start from 0, go forward by 2 will give you all of the even indices, and start with 1 and go forward with 2 will give you all the odd indices.
3, 5, etc. And then we need to add the batch dimension to this tensor so that we can apply it to the whole sentences, so to all the batch of sentence, because now the shape is sequence length to the model, but we will have a batch of sentences. So what we do is we add a new dimension to this PE, and this is done using unsqueeze, and in the first position, so it will become a tensor of shape 1 to sequence length to the model. And finally, we can register this tensor in the buffer of this module. So what is the buffer of the module? Let's first do it. Register buffer. So basically, when you have a tensor that you want to keep inside the module, not as a parameter, learned parameter, but you want it to be saved when you save the file of the model, you should register it as a buffer. This way, the tensor will be saved in the file along with the state of the model. Then we do the forward method. So as you remember from before, we need to add this positional encoding to every word inside the sentence. So let's do it. So we just do x is equal to x plus the positional encoding for this particular sentence. And we also tell the model that we don't want to learn this positional encoding because they are fixed. They will always be the same. They are not learned along the training process. So we just do it requires grad false. This will make this particular Spencer not learned.
Yeah.
And then we apply the dropout. And that's it. This is the positional encoding. Let's have a look at the next module.
Okay, so before he moves on, let's just sort of digest the last 5 or 6 lines or so. We calculate the position, we calculate the diff term, which is uh, the denominator for any PE matrix, so create a matrix of shape, all the vectors, of course, PE for all the vectors, seq length by D model. So each row of the PE matrix is one single embedding for a position. So 0 for token number 0, token number 1, token number 2, so on and so forth. So for all of these, so for all of the rows, right, before the comma, and now we're doing the columns for all of the rows. So for the first line, for all the even indices in a single row, you want to do the sine of the position times the diff term, which is just pos over 10,000 to the power of 2i upon D model, which is what's done here. And then, of course, for all of the even, all the odd indices, we just do the cosine. Yeah, so that makes sense. And then we just unsqueeze the PE matrix so that we sort of create like a batch dimension. I believe the one is the batch dimension. And then we registered this matrix because it's literally, we can use this matrix for any transformer that has the same D model, which is the dimension of the model, and when we want the same sequence length. That's why we registered it as a buffer so that it can just be loaded when we load the model. And then the forward is nothing but the input embeddings, X, the input embedding matrix, X plus self.pe until the X shape 1, which is important because um, X, as we know, is the input embedding space, and the embedding has dimensions vocab size by D model. So this is kind of hard to parse. So of course we want all the rows in the sequence length because the sequence length will always be lesser than the vocab size. For the D model, we want, yeah, this is difficult to parse. So of course, no step, we want all of those things. We want the embedding. I think we need to visualize this. So let's say the embedding matrix, input embedding matrix is something like vocab size equals something like 100,000 and D model, which is 512. And then we have the position embedding matrix, which is the model columns, which is 512, and seek length rows, which is something like, let's say, 40 sequences or 40, yeah, 40 tokens per sequence, right? We want this stuff to be added per 40 tokens in the input embedding matrix. Actually, input embedding matrix. Oh, the input embedding matrix is not vocab size. This is just the embedding that we, this is just the embedding matrix that we take these embeddings out of. The input embedding is dependent on the sequence length as well, um, I believe. Yeah, forward X would be integers here, given an array of integers here, so like given by the tokenizer. So I really love transformers would be, let's say, 0 1 2 3 4. That 0 1 2 3 4, 0 would be looked up in this embedding matrix. That vector would be pulled out, added to this, well, matrix. 1 added below it, 2 added below it, and so on and so forth. So it would be 5 tokens by 512 like 512 numbers, which is the dimension of the model. So it would be 5 times 512. And when we add position encoding vectors, we only want it until the shape, or until the sequence length. So it has to be at least the sequence length of the positional encoding. Yeah, this does not make a ton of sense to me. X equals X plus. So if we're doing plus, we can assume that it has to be the same dimensions. These matrices have to be the same dimensions. So X is obviously um, sequence length, or let's say, actually, it can be greater than sequence length. Yeah, yeah, yeah. Sequence length is almost like the context window of the mate of the transformer. Is that right? Sequence length is a sequence length of, that's where ChatGPT comes in. I'll obviously use my software, which I built, is the best um, dictation software in the world, I believe, um, and I have it on good authority. So all you need to do is something like, let me, yeah, we're sort of asking about this code snippet right here. So let me add that. Um, this is a code snippet for calculating the positional encoding, positional embedding in transformers. The X is the original input embeddings, and the PE is the position embedding matrix. How does this code make sense? Can you sort of deconstruct the torch numpy matrix notation in this equation? So we did that, and then it's sort of transcribing. It does that, and yeah, let's see what ChatGPT says. Okay. Oh, wow. Yeah, batch size is 1. Sequence length demodel. Batch size 1. Max length demodel. Understand slicing notation. In the first dimension, keep the single batch dimension since self is stored with PE. In the second dimension, slice only the first sequence length positions. The sequence length of third dimension, take the entire embedding dimension, which is the D model, of course. So after slicing, the shape of this term is 1 sequence, okay. Broadcast addition, X of the shape, okay. Has shape this. What we do is this. Um, does does the sequence length of the positional embedding matrix determine the context window of the model? Oh, exactly. Oh, amazing. So yes, let's go. How many tokens it can process at once? Great, amazing. So the yep, largest max length you can pre-compute position embeddings for is the maximum context window. Max length, okay. Okay, what happens if you exceed it? If sequence length is greater than max length, then you'll either get a runtime error index. Oh, you're slicing past what exists. Or if you coded it loosely. Huh. Okay. So if the sequence length of the input embeddings somehow overrides the oh oh wow. I see. Okay, this makes sense. I see. So the upper limit of how many tokens we can process at once is the max length of the positional encoding matrix in this case. So it would have to be at the order of not 40 like I mentioned, but something like 40,000, right? Because if we want to encode, let's say, so that would mean, especially on a word level tokenizer level, it would mean 40,000 tokens, which would mean 40,000 words, which is like a book and a half. I think that's a pretty good context window. Okay, this makes sense. So, so what is a common max length of a position embedding matrix in the vanilla transformer? To 512 tokens. So any sequence that they wanted to translate could not exceed 512 tokens, whatever that meant and however they were tokenizing their sentences. Okay, Llama 2K, GPT-4 128K. Of course, Gemini somehow has 1 million um, token context window. So their position embedding matrix looks something like 1 million rows and whatever the dimension of the model is, which only gets higher. Um, let's actually ask that. What is the dimension of the model in the Gemini Pro series? I know they have a 1 million token context window, which means 1 million rows in the position embedding matrix. What is the dimension of the model? Yeah, this animation I sort of built myself, which is pretty cool. Um, oh, wow. This is difficult. Model dimensions ranging from a few thousand to well over 10,000. Fantastic. Okay. There's no confirmed data. What? Of course there's. Gemini 1 million context window. Yeah, there you go. 1 million or more tokens. Yeah, there has to be like architectural advancements here. In practice, 50,000 lines of code, 80 characters per line, all the text you have sent in the last 5 years, 8 average length English novels. So you were just discussing a novel. Like 40,000 tokens is a lot because, like, let's actually do that. How many words in an average English novel? Okay, 70,000 to 100,000. I was sort of short on that. So 40,000 would mean half an English novel. Obviously, theirs is 8 times that. which would land you at around 320,000 tokens if you're doing it by word. But of course, more sophisticated tokenizers don't do it by word, they do it by subword tokenization. So something like transformers could possibly be uh, uh, split into transform and ers. Or if I were to think about like something like um something like doppelganger, like like a long word, it could possibly be broken down into do, pull, gang, so like one word can create four tokens in that sense. Wow, that's kind of sick. Yeah, this is nuts. Um, this is nuts. 1 million context is crazy. Okay, so we have that. Yeah, they must be using rope or something because rope being rotary position embeddings, which we hopefully will get to learn later. But there is Gemma source code available, GitHub source code. Yep, there you go. Gemma 3. Yes. Oh, I think it's this one. Open weight, Gemma, multimodal. Okay. GM, NN, Gemma 3N. Of course. Okay, yeah. There it is. Transformer.py. This is where they defined much of their model, I believe. Uh, yeah. Yeah, there you go. This is the configuration of the model. And yeah. Oh. Merge embeddings, encode vision. Yeah, vision transformers are a whole different deal and super fun to learn. Gemma 3 and .py pattern. Yeah, 4B. Oh, so the only things that really change are the number of hidden dimensions and the number of layers, which I assume is the number of transformer blocks, which we will also get to know later. Okay, cool. Let's keep going.
Okay, we will build the encoder part of the transformer, which is this left side here, and we still have the multi-head attention to build the add and norm and the feed forward. And actually, there is another layer which connects this skip connection to all these sublayers. So let's start with the easiest one. Let's start with layer normalization, which is this add and norm. As you remember from my previous video, let's have a look at the layer normalization.
We forgot to build. We forgot to code up the position embeddings. Okay, let's do that now. So the arguments were dropout, I believe, which should be an integer, and then there was something else. I forget. Okay, and then forward was x equals x plus pe, um, all of the batch dimension, and then un anything until the dimension of x shape 1, which is just like number of tokens in the input space, which means something like x dot shape 1, and then all of the D model, uh, PE, then return dropout, dropout uh, X. Obviously, actually, this would be self dot dropout. Self dot dropout equals nn dot dropout, dropout. Yeah, and then we also need self dot pe equals torch dot torch dot torch dot Uh, arrange. Um, no, this is torch or tensor, I suppose. Oh, yeah. Actually, torch dot tensor. Bash dimension one. Self dot torch dot arrange. No, torch dot. I think it's tensor. Um, one, which is the batch size, sequence length, sequence length, which is also an int, of course, and d model, which is also an int, obviously, sequence length, d model. What is that? Data type is float, data device. How do you define this? Shape, I think, is important. Could it be a range? Start, end. No, no. I need like dimensions, I suppose. Shape. I think it's random. Torch dot random. No, it's not random. We need it to be deterministic. Uh, man. Oh, I forget. Okay, let's just make it so that it's dot torch dot array as array. No, arrange. This is wrong. Cooked. Let's just do tensor. No. Okay, let's comment this out for now, for my own sanity. Uh, self dot pe. This would be self dot pe. Uh, self dot pe. And we also need what? Could it be like a shape argument? No. Let's see what it's built of. Data, data type, non-device. Ah, okay. So I can't use this for sure. It's not tensor for sure. Because we were defining the shape of the object. Oh, we can just do, we can just do arrange, start, end. No. Does arrange have a shape parameter? Out. Self.pe. And there was self dot div term, self dot position. Um, self dot position was just self dot div term was self dot exp times self dot position. Say it's this. Let's also say self dot p somehow this. There you go. Oh no. Oh no. Random size. Okay, let's just do that for now. This is driving me nuts. D model. Um, Position. Let's also do that for this, but the position would just be uh, one single line. Tensor is not callable. It's not self.ext, it's torch.ext. Um, Position times math dot log 10,000 dot float. This is negative y dot float. Let's just do this. Times actually divided by d model. Divided by d model. Um, yeah, so we need this and this. Self dot position. Position is this. Mm, Yeah, so self dot even would be self dot even indices would be something like I need to figure out the syntax for PE. This is difficult. Um, okay, torsion zeros, of course, of course. Could have done ones or zeros. Seek length D model. Torch dot zeros. Oh, uh, zeros. Size is one seek length D model. Vector of shape seek length. Oh, because the position vector is 0, 2, 4, 6, 8, 10, and stuff. It's actually 0, 1, 2, all the way to uh yeah, seek length. Yeah, that's right. And squeeze would mean uh yeah, lifter range. Torsion range. 0 to D model to the size, I believe. Oh, size. Yeah, it's a union of integers. Okay, all right. The position would mean a range uh, from 0 to sequence length with gaps of 2. Uh, self.div term would then mean something like torch dot self, actually torch dot arrange, um 0 to d model to float. Yeah, that makes sense. So we would need a list from 0 to d model, skipping two, um I'm not needing this. Yeah, skipping this, uh and then dot float. Yeah, position. Um and what do they do for like the, oh, they just apply it in place for the sine and cosine. Okay, d type equals torch dot float dot unsqueeze one. Okay, I don't really get this. Position, for each position, PE is sequence length by d model. So for each position, why is it from 0 to seq length? It should be 0 to d model, no? Oh, no. Uh, seek length. Uh, okay, vector of shape seek length by 1. Oh, yeah, position, of course. So the position would mean uh this is this is not by step of 2. It should be 0, 1, 2, 3, 4, how many ever tokens are in the sequence, and the d type should be torch dot float. I think, right? Yeah, and then unsqueeze to be become column vector. So unsqueeze 1, because we need the column dimension to become uh, unsqueezed, suppose. And then PE matrix, all rows, but only uh, the even indices. Why is this bad? Oh, self.pe equals sign torch dot sign. What? Okay, torch dot sign position times self dot position times self dot diff term. I wonder why this would be 2, this would be 1, this would be cosine. Drop out. Oh, this would be PE, I suppose. Yeah, I don't think it's like a self sort of. Okay. Yeah, it's not a self sort of yeah, PE position different because they're like temporary variables almost. And then we do need to unsqueeze PE. So it becomes like it adds a batch length dimension to it. Um okay. Self.PE. Oh, very cool. Okay. But here the self.PE is not a self thing.
This particular tensor not learned.
Funny.
And then we apply the dropout.
Yeah, PE is not a self parameter. That is nuts. So I suppose we do put self.pe. because we should. Self.pe. Okay. Okay. And then we do self.pe dot unsqueeze 0 um 1 which is batch size 1 seek length d model, right? And here it's just updating PE matrix with sinusoidal positional embeddings. This is even indices of each PE vector, and this would be odd indices of each PE vector. PE is this is PE dimensions equal um, seek length the model uh, arrange column vector of positions uh, seek length 1 would be something like whatever, like 0 1 2 3 4, uh basically this context window size transposed, so column. And then the diff term is just oopsie, it's just 1 over 1,000, sorry, 10,000 um times, so you would do this then. Oh, okay, 10,000, actually do this over 10,000 times 2I over d model. Yeah, this adds up. And then, yeah, we multiply that by position and then do the sign, and that sounds good. Okay, all right. I can then delete this just for demonstration purposes, and then we can move forward.
And that's it. This is the positional encoding. Let's have a look at the next module. Okay, we will build the encoder part of the called the gamma. Let's side here, and we still have the multi-head attention to build the add and norm and the feed forward. And actually, there is another layer which connects this skip connection to all these sublayers. So let's start with the easiest one. Let's start with layer normalization, which is this add and norm. As you remember from my previous video, let's have a look at the layer normalization, a little briefing. So layer normalization basically means that if you have a batch of n items, in this case only 3, each item will have some features. Let's say that these are actually sentences, and each sentence is made up of many words with its numbers. So this is our 3 items. And layer normalization means that for each item in this batch, we calculate a mean and a variance independently from the other items of the batch. And then we calculate the new values for each of them using their own mean and their own variance. In the layer normalization, usually we also introduce some parameters called the gamma and the beta. Some people call it alpha and the beta. Some people call it alpha and the bias. Okay, it doesn't matter. One is multiplicative, so it's multiply.
The gamma is missing from this equation. It usually is like dot gamma, and just a scalar to add sort of scaling information. And yeah, and there's always a beta parameter. Actually, beta is also missing here. Okay. This epsilon here, I think, is also a parameter, a learnable parameter. But yeah, this is basically calculating the z-score. If you just discount this e thing here, it's just the z-score of um xj.
By each of these x, and one is additive, so it's added to each one of these x. Why? Because we want the model to have the possibility to amplify these values when he needs this value to be amplified. So the model will learn to multiply this gamma by these values in such a way to amplify the values that it wants to be amplified. Okay, let's go to build the code for this layer. Let's define the layer normalization class.
Also, layer norm is probably not the state of the, like, is not the norm of choice for a lot of transformers now. They mostly use RMS norm. There are some transformers like the differential transformer developed by Microsoft that does group norm, which was one of the few times I've seen group norm be applied. Of course, there are like fantastic visualizations for layer norm, and RMS norm, group norm images. Yeah, there you go. It's actually from the PyTorch documentation, I believe. I shouldn't say that without double checking, so I'll do that now. Layer norm torch. Yeah, yeah, something like that. Oh, that's not ideal. Okay. Um, yeah. So batch norm is across the batch dimension, I believe. So it takes something from each of the batches. A layer norm takes something from each layer. So C stands here for like channel. So height, width, let's say, and this is a layer. This is another layer. This is another layer. So layer norm does the norm of a single layer. Instance is a single sort of, I think it's within like a row or a column of a layer. And then group norm is distributing the layer into groups. So of course here a layer is distributed into groups of two. So this is one group norm. This would be another group norm. And yeah, uh, n just happens to be the number of batches. C is, I believe, um, what is C actually? Oh, C might be the number of channels. N might be the number of, well, height width. This would be one layer. C is the number of channel access. Yeah, N is the batch access. So um, N has, so of course this sort of tensor has 1, 2, 3, 4, 5, 6 batches. Channel access is HW pixels. So C is basically just H times W, I suppose, or like just representative of a single layer. So C equals 1 is the first, C equals 0 is the zeroth layer, which is the first layer. C equals 1 is the second layer, and so on. Um, yeah, 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 which is why N is basically, yeah, when N is 0, it's taking from the 0th instance of each of the batches. And when N is 1, the first instance of each of the batches, so like right here, N equals to 2 would be something right here, and so on and so forth. So it just moves that way. Um, yeah, cool. I do want to stop uh, and sort of reflect on norms as well. So let's do that.